Myself Vivek Kumar. I will be explaining now Babel Routing Protocol. So in this slide you can see these are the topics that I will be covering now, like routing protocol, what exactly is Babel Routing Protocol, how distributed Bellman-Ford algorithm work, what is transient loop in Bellman-Ford, how feasibility condition work, why do we need it, what is starvation, and how will we solve the starvation using sequence routing. So these are the topic I will be explaining. So let's start with routing. So what exactly is routing? Routing is a process in which the layer 3 device finds the optimal path to deliver a packet from one network to another network. Since there are multiple routes available to transfer packet from source to destination, so there are different protocol is built to achieve this goal, called as routing protocol. So routing protocol uses software and routing algorithm to determine optimal network data transfer and communication path between network nodes. So these are the example of routing protocol like RIP, IGRP, OSPF, BGP. Routing protocol is mainly of two types: static routing and dynamic routing. So each router mainly maintain a routing table. Okay, so based on that, static routing which doesn't change routing table unless network administrator modifies them manually. And in dynamic routing, it changes routing table according to if there is change in a topology. Suppose some connection got broken, then according to that, routing table gets changed or it will get updated. And static routing is more secure as compared to dynamic routing. Static routing provide high security. So in this diagram you can see there are mainly three types of dynamic routing, like distance vector, link state, and hybrid. So for this topic, mainly distance vector is very much required to understand Babel. So what is distance vector routing protocol? A distance vector routing protocol in network determines the best route for data packet based on distance, and these are the features of it. So these are the features that a router follow, like update of the network are exchanged periodically. So after a fixed duration of time, the whatever the update is there, like whatever the update, like if a connection got broken or some kind of problem is there, it get updated periodically, and updates are always broadcasted. And to broadcast the update, like full routing tables are sent in the updates. And this is the fourth point is very important, like router always trusts routing information received from neighbor router, like so this is also known as routing on rumors, and this leads to a problem which will be see ahead. Is a loop avoiding distance vector routing protocol that is designed to be robust and efficient both in wireless mesh network and in wired network also. So the distance vector routing protocol, it is based on Bellman-Ford algorithm, which I will explain in a second. And this algorithm has an additional mechanism named feasibility condition that guarantees good transient behavior, which is also I am going to discuss in a second. And apart from these two, Babel can carry routes for multiple network layer protocol. Like it works fine for IPv4 and also IPv6. So it works for algorithm. So before that, we need to know two things. Like for every pair of neighboring node A and B, Babel compute an abstract value known as cost of the link from A to B. And given a route between any two nodes, it does not need to be neighboring nodes. The metric of the route is calculated, and the metric of route is sum of the cost of all the link along the route. And the goal of the routing algorithm is to compute the lowest metric to S. Okay, so let's understand the algorithm. So every node A maintains two pieces of data. Its estimated distance to S, which is denoted as D of A, and its next hop router to S, which is written as NH of A. So initially D of S is 0, like distance of S from S is 0, and D of A is infinite, and all other node other than S will be infinite. And NH of A, a next hope router of A is still undefined. Okay, So what will happen now? B will broadcast D of B to its all the neighbors. So when let's say A receives D of B information, so it will check if its next hop is equal to B, then it will simply get updated by adding the cost of link between A and B. And if it's not the case, then it will check whether this path is more feasible or not, like more lower in this path is lower in cost or not. So if it's lower in cost, like the cost link between A and B, and D of B is less than D of A, then it will update itself, and it will update similarly, it will update next hop router to B. So what happen if NH of A is equal to B and B stop broadcasting due to some reason? In that case, D of A will again reset to infinity, and NH of A, it will be undefined. And in this example, the cost of each link is 1, and S is our source which we need to find for each and every other node. So initially the distance is 0 for S, and for other node it's infinity. So now it broadcast the information to A. So A checks, okay, so the cost of link is 1, so initially it has infinity, so it will check 0 plus 1 is less than infinity. Okay, so it is less than infinity, so it will update its it will matrix to 1, and also it will update its next hop to S, and other remaining will be infinity. Similarly, in next iteration, B and C will receive the information of A when A will broadcast that when A will broadcast its matrix to B and C. So similarly, B has initially infinity matrix and C has also infinity matrix. So it will check the matrix score of A, which is 1 plus the cost of link between A and B, which is also 1. So 1 plus 1 2, which is definitely less than infinity. So it will get updated. So it will get updated by 2, and its next hop for B will become A. And similarly in C also it will become 2, and its next hop will become A. And again in next iteration we will check. So there will be no change. All the results will be same. All the metrics for nodes and its next hop is same. So we have reached to the convergence point. So we don't need to move ahead. And we have got our transient loop and how does it form. Okay, so naive application of Bellman Ford to distributed routing can cause transient loop after whenever a topologies get changed. So after convergence, we have seen the matrix of B and C is equal to 2, and next hop of B and C is also equal to A. So now suppose the link between S and A fails, which can be seen in the diagram. So when A detects the failure of the link, A knows it can no longer reach to S, but B is still broadcasting matrix of B to A. So A sees that B is telling that it is at distance of 2 from A. So A switches its next hop to B, and A broadcasts a matrix equal to 3, which is nothing but the sum of matrix of B and cost of the link between A and B. B sees the matrix of A is changed, which is the next hop of, and B is also the next hop of A. So according to Bellman Ford, B will update its matrix. Then again A will update its matrix since B is its next hop. Similarly again B will update, and again A will update, because each other are matrix, each other are like A and B are next hop of each other. So a loop is getting formed, and this process of node changing selected neighbors and increasing their metric continues until the broadcast matrix reaches to infinity. So once it reaches to infinity, it will stop, and all this has formed a loop, which Babel will solve using a feasibility condition. So now which I am going to understand the feasible condition which will solve tangent loop problem in Bellman Ford. So Babel router will discard received route announcement unless they can prove that accepting them cannot possibly cause a routing loop. So Bellman Ford is robust, and we can ignore update if they risk generating a loop. So if there is a broadcast from its neighboring node, and if there is a chances, then it can form a loop. So it will discard that. Announcement. So let's say for a given router A, we are introducing feasibility distance, and feasibility distance will be written as FD of A, and it is defined as the smallest matrix that A has ever advertised for source to any of its neighbor. So which will be feasibility distance. So what's going to happen now, that so an update sent by a neighbor B of A is feasible only when matrix of B is less than feasible distance of A. So we are adding this condition to the Bellman-Ford algorithm. So okay, so you can see here when it checks that the next hope is B or not, then we will check also that if matrix of B is less than feasible distance of A. If that's the case, then it will update. Similarly, in next case also we are adding this condition. So this condition actually ensures that loop never we can see we have feasibility distance and matrix of A, B and C, and there is a disconnection between S and A. So when A receive the broadcast by B, which is the matrix of B, then it will check whether the matrix of B is less than feasible distance of A. So here the matrix of B is 2 and feasible distance of A is 1. So 2 is less than 1. This condition does not hold true. So it will not receive, it will not consider that announcement, and it will discard it, and it will reset its matrix to infinity. Similarly, other iteration will happen, and a B and C will update its matrix to infinity because there is change in matrix of A, and for B and C, A is its next hop router for both B and C. So there will be updation in each iteration, and the matrix will become infinity for all these three nodes. Okay, so everything seems good, but there is a problem in feasibility condition. It leads to starvation. So we will see how it happens. So what exactly is a starvation? So when so it is defined as like it causes when starvation when a router run out of feasible routes. So like it has no feasible route to route to source. So it leads to starvation. So in this diagram you can see we have matrix of A and B and its feasibility distance, and now take that the link between A and S get breaks. So now A will check that the matrix of B is less than feasibility distance of A is so it will check this condition. So for this case also it does not hold true. The feasibility distance of A is 1 and the matrix of B is 3. The matrix of B is 2. So it will the condition does not hold true. So but it is clearly visible that there exists a clear path from A to S through B, but due to the feasibility condition it will not consider that broadcast, it will not consider that announcement, it will simply discard. So eventually A will suffer from starvation. So to solve starvation, there are different techniques. One of the technique is like when no route is available, then reboot the whole network, but it takes a lot of time to do that. So sequence routing number is introduced to solve the starvation problem. So what happened? A sequence number is assigned to the route. Like every route carries a sequence number which is a non-decreasing integer that is propagated unchanged throughout the network, and it is only ever incremented by the source. So let's say a pair S comma M, where S is the sequence number and M is the matrix, is called a distance. So if feasibility distance of A is S comma M, and update carrying the distance S dash comma M dash broadcasted by B is feasible only when the condition is that s dash should be greater than s, or s is equal to s that, and m dash is less than m. So it's basically says that it should be more recent. The sequence, if the sequence number is greater, then it will accept that, it will consider that that broadcast, and it will update. To conclude all of this, Babel is a robust and flexible routing protocol. It is resilient for both wired and wireless network. It's a great framework for experimenting with new ideas. It is source specific routing, it is radio interfaces sensitive matrix, it is delay based routing, and all of the Babel work is documented in 3 IFC on the internet. You can, and available as open source software also. So for in-depth knowledge, the paper can be referred.